Direction ratios and direction cosines. Welcome, everyone. Today we are diving into a fundamental aspect of 3D geometry. When we study vectors in three-dimensional space, we usually start by looking at their magnitude, that is, how long the vector is. However, knowing the length isn't enough to fully describe a vector's position. To truly understand a vector, we must also describe its precise orientation, or the specific direction in which it is pointing, relative to our x, y, and z coordinate axes. To help us do this mathematically, we use two closely related concepts which we will explore in detail today: direction cosines and direction ratios. By the end of this lesson, you'll see how these two tools allow us to pinpoint any direction in space with absolute precision. Understanding direction cosines, DCs. Now that we've introduced the importance of orientation in 3D space, let's dive into the first key concept: direction cosines. To visualize this, I want you to imagine a vector. Let's call it a vector, starting right at the origin, point O, in our three-dimensional coordinate system. As this vector extends out into space, it doesn't just point randomly. It forms three specific, measurable angles with the positive directions of our three axes: the x, the y, and the z axes. To keep things organized, we use the Greek letters alpha, beta, and gamma to denote these three angles respectively. Now, here is the crucial part. We aren't just interested in the angles themselves, but specifically in the cosines of these angles. These values, the cosine of alpha, the cosine of beta, and the cosine of gamma, are what we officially call the direction cosines of the vector. In mathematical notation, to make our work easier later on, we typically represent these three cosines using the letters L, M, and N specifically. L equals the cosine of alpha, representing the angle with the x-axis. M equals the cosine of beta, for the angle with the y-axis. And N equals the cosine of gamma, for the angle with the z-axis. Keep these definitions in mind, because as we will see in the next slide, these values share a very special mathematical property. Important property of direction cosines. Now that we have defined what direction cosines are, specifically, the cosines of the angles the vector makes with the x, y, and z axes, there is one vital mathematical rule you must always remember. This property is a fundamental characteristic of direction cosines. If you take each of these direction cosines, L, M, and N, square them, and then add them all together, the sum will always be exactly equal to 1. In mathematical terms, we express this as L squared plus M squared plus N squared equals 1. Keep this identity in mind, as it serves as a perfect way to check if your calculated direction cosines are correct. Understanding direction ratios, doctors. Now you might be wondering, if we already have direction cosines, why do we need another concept? Well, as we saw in the previous slide, direction cosines are tied to the cosines of specific angles. Because these values are bounded between -1 and +1, they often result in very messy decimals or complicated fractions that make your algebra much harder than it needs to be. To make our lives easier and simplify our calculations, we introduce something called direction ratios. If you look at a standard vector, let's call it vector A expressed in terms of its components, a sub 1 I hat plus a sub 2 j hat plus a sub 3 k hat, the scalar components. That is, the numbers a sub 1, a sub 2, and a sub 3 are actually called the direction ratios. But here is the key thing to remember. Direction ratios don't have to be unique. They are simply any three numbers that are proportional to the direction cosines. To put this mathematically, if we let L, M, and N represent our direction cosines, then any set of numbers a sub 1, a sub 2, and a sub 3 will serve as direction ratios as long as the ratio of a sub 1 over L equals a sub 2 over M, which equals a sub 3 over N, all being equal to some constant. Let's call it K. In the next slide, we are going to see exactly how we use this proportional relationship to bridge the gap between these ratios and the cosines. The relationship between doctors and DCs. Now that we understand that direction ratios are simply any numbers proportional to our direction cosines, let's look at how these two concepts are mathematically linked. Think of it this way. The direction cosines are essentially the direction ratios normalized by the magnitude of the vector. In simpler terms, we take those direction ratios and scale them down so that the resulting vector has a length of exactly 1. Let's look at the math behind this. Suppose we have a vector, let's call it A, which is composed of its components, a sub 1 I hat plus a sub 2 j hat plus a sub 3 k hat. To find the direction cosines, we first need the magnitude of this vector, which we denote as the magnitude of A. We calculate this by taking the square root of a sub 1 squared plus a sub 2 squared plus a sub 3 squared. Once we have this magnitude, finding the direction cosines is straightforward. The first direction cosine, L, is simply the first component, a sub 1 divided by the magnitude of A. Similarly, M is a sub 2 divided by the magnitude of A, and N is a sub 3 divided by the magnitude of A. Because of this relationship, there is a very beautiful consequence. The unit vector, which we write as a hat, represents a vector in the same direction as A but with a magnitude of 1. As you can see here, this unit vector can be expressed directly using our direction cosines. It is simply L I hat plus M j hat plus N k hat. This connection is vital because it shows that the direction cosines actually provide the blueprint for the vector's orientation in space. Real-world application, aviation and navigation. Now that we have mastered the mathematical definitions and the relationship between direction ratios and direction cosines, let's step out of the textbook and see how this actually works in the real world. Think about aviation. When a pilot is flying an aircraft, they aren't just moving in a straight line on a flat map. The plane is moving through three-dimensional space. It has forward momentum, but it also has lateral movement and changes in altitude. We can represent the plane's flight path as a vector. Specifically, things like the heading, which is the compass direction, and the climb angle, which is how steeply the plane is ascending, are all components of that 3D vector. This is where our topic becomes incredibly powerful. A flight computer uses direction cosines to break down the plane's total velocity into its specific components. By using these cosines, the computer can calculate exactly how much of the plane's speed is contributing to movement along the north-south axis, which we call the x-axis, the east-west axis, or the y-axis, and finally, the altitude or vertical axis, which is our z-axis. It's essentially using the math we just learned to navigate the skies. Now, let's put this theory into practice with a concrete, step-by-step numerical example. Step-by-step example. Now that we have covered the theory and the relationship between these two concepts, let's put everything we've learned into practice with a concrete example. Here is our problem. We need to find both the direction ratios and the direction cosines for the vector, A, which is defined as 2I hat plus 3, j hat plus 6k hat. Let's break this down into 3 clear steps. Step 1, identifying the direction ratios. As we discussed in the previous slides, the direction ratios are simply the scalar components of the vector. Looking at our vector, we can see the coefficients for each axis are 2, 3, and 6. Therefore, our direction ratios, or doctors, are simply 2, 3, and 6. Step 2, calculating the magnitude of the vector. Before we can find the direction cosines, we need to know the total length of the vector. To do this, we use the magnitude formula, which is the square root of a sub 1 squared plus a sub 2 squared plus a sub 3 squared. Plugging in our values, we get the square root of 2 squared plus 3 squared plus 6 squared. When we calculate the squares, that gives us the square root of 4 plus 9 plus 36. Adding those together, we get the square root of 49, which simplifies perfectly to 7. Step 3, calculating the direction cosines. Now we apply the formula we learned earlier, where each direction cosine is the corresponding direction ratio divided by the magnitude. So, for our first component, L equals 2 over 7. For our second component, M equals 3 over 7. And for our third component, N equals 6 over 7. So our final direction cosines are 2 over 7, 3 over 7, and 6 over 7. Notice how these values are all between -1 and 1, which satisfies the property we discussed in slide 3. As we move to the next slide, I want you to pay close attention to some common pitfalls where students often trip up during this exact process. Common mistakes to avoid. Now, before we wrap up with our final summary, I want to pause and discuss some common pitfalls. I've seen many students stumble on these specific points during exams, so please pay close attention. First, a very common mistake is confusing direction ratios with direction cosines. It is easy to use these terms interchangeably in your head, but mathematically, they are quite different. Remember, direction ratios can be any real numbers, for example, 2, 3, and 6. However, direction cosines are much more restricted. They must always fall between -1 and +1, and they must satisfy the fundamental property we discussed earlier. L squared plus m squared plus n squared equals 1. Second, watch out for forgetting the magnitude. When you are performing the conversion from direction ratios to direction cosines, just like we did in our step-by-step example, beginners often forget to divide each component by the magnitude of the vector, which we denote as the magnitude of a with a vector arrow over it. You simply cannot find the correct direction cosines without first calculating the total length of the vector. Finally, be careful with sign errors. It is important to remember that both direction ratios and direction cosines can be negative. If you see a negative sign, don't assume it's a mistake. A negative value simply indicates that the vector is making an obtuse angle, that is, an angle between 90 degrees and 180 degrees with that specific axis. Keep these 3 points in mind, and you'll avoid the most frequent errors. Now, let's move to our final slide to consolidate everything we've learned today. Key takeaways. First, let's revisit direction cosines, or DCs. Remember, these are the values L, M, and N, which represent the cosine of alpha, the cosine of beta, and the cosine of gamma. A crucial point to keep in mind, and one we saw in our property slide, is that these values must always satisfy the equation. L squared plus m squared plus n squared equals 1. Next, we have direction ratios or doctors. These are the scalar components, a sub-1, a sub-2, and a sub-3 of a vector. As we discussed, these are simply any numbers that are proportional to the direction cosines. Now, regarding the conversion between the two, if you are starting with direction ratios and need to find the direction cosines, the process is straightforward. You simply divide each direction ratio by the magnitude of the vector. In mathematical terms, L equals a sub-1 divided by the magnitude of A. Finally, let's look at the unit vector. The unit vector in the direction of vector is simply the vector formed by using its direction cosines as the components. We write this as a hat equals L I hat plus M J hat plus N K hat. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the key takeaways from today's session to ensure everything is clear. If you can master these relationships, you'll have a solid foundation for working with vectors in three-dimensional space. Great job today.